Good morning, girls. Welcome back to the revision session of Unit 2, Part 2, that is software design. So, in the previous session, we had covered the overview of design process and how to characterize a design. Okay, now let us continue with the next topics. Okay, so coming to the characteristics of a good design. So, generally, a good design is having four different characteristics. They are nothing but the correctness, understandability, efficiency, and maintainability. Okay, these are the four characteristics that will decide whether a design is a good design among various alternate designs. Okay, so among these four characteristics, understandability is a major concern. We need to much bother about the understandability. Okay, so now let us see what characteristics of a design solution will make it easily understandable. The first one is use consistent and meaningful names to various design components. So generally various design components, in the sense, in the design phase the various components are nothing but the modules, and within the modules we are having the functions and various data items. So whenever you had identified the module, and whenever in the module when there are a set of functions and certain data items, for all these modules, for all these functions, and for all these data items, we should give a relevant meaningful names. Okay, so just by seeing the name of a function, we will be able to identify what kind of functionality that particular function performs. For example, you are having a function, you had given a name for a function sorting, so it indicates that that particular function will perform sorting. Okay, if suppose instead of sorting I had given the name to that function like function A, can I understand just by seeing that name of that function? Can I understand what that function do? No. Unless I go into the code of that particular function, unless I trace the code of that function, I can't understand what is the major functionality or what are the services that are provided by that function. Okay, so that is the importance of providing meaningful names to all the design components. The next one is it should make use of abstraction and decomposition principles in good measures to simplify the design. Now, how to get this abstraction and decomposition principles? Okay, how to get this abstraction and decomposition principles? Why are abstraction and decomposition principles used in design? So these principles are used because to make design modular and layered. That means in order to get abstraction and design principles in a design, we should have a modularity and layered arrangement among the design. So that means we can say a design solution is easily understandable if it uses consistent and meaningful names to various design components, and if the design is modular and the modules are arranged in distinct layers. That's nothing but the layered arrangement of modules. Okay, so whenever a design solution is having this modularity and layered arrangement of modules, then we can say that design solution is understandable. So now we need to know what is this modularity and layered arrangement of modules. Okay, so coming to the modularity. A modular design is an effective decomposition of a problem. A modularity is a fundamental characteristic of any good design. So here the problem is decomposed into modules that have only limited interactions. So here divide and conquer principle is used for decomposition. So in the modularity, we need to decompose the modules in such a way that is you are provided with a problem. Now that problem is decomposed into certain modules. Okay, this decomposition is done based on divide and conquer principle, and during this decomposition, the decomposition should be done in such a manner that there should be limited interactions among the modules. Okay, the modules are almost independent of each other. That is, whenever you are having a modularity, that is, whenever there are less interactions among various modules, then each module will be easily understandable. That means if the module is independent from each other, then it will be easier for us to understand. So to understand why this is so, remember that it is very difficult to break a bunch of sticks, but it is very easy to break the sticks individually. That means if all the modules are grouped together, and if somebody asks you to understand understand those modules, then it will be difficult for us to understand. But if these modules are divided in such a way that there is very less dependency among the modules, then we can understand them properly. Okay, so that means it also reduces the complexity while understanding. Next, coming to the layered design. A layered design is one in which the call relationships among different modules are represented graphically. Finally, it would result in a tree-like diagram. So, this layered design is concentrating on the control relationships among the modules. The control relationships among the modules should be represented in a proper manner. That should be represented in a tree-like structure. Okay. So, why this tree-like structure? That let us see in the next PPT. Okay, next slide. The modules are arranged in a hierarchy of layers. Whenever the modules are arranged in a hierarchy of layers, a module can only invoke the functions of the modules in a layer immediately below it. The neat arrangement of modules in a hierarchy means implementing control abstraction. So here control abstraction in the sense the lower modules is unaware of higher layer modules. That means a module in the higher layer can know that there is a module in the lower layer. Why? Because a module in the higher layer only can make a call to the module in the lower layers. And it should not happen in a reverse manner. That is, a module in the lower layer should not be aware of the presence of a module in the higher layer. That means a module in the lower layer should not have a capability to make a call to the module that is present in the higher layer. Okay, so that's what control abstraction is. Okay, so there should be only one way of call relationships among the modules. If at all we are having a two-way call relationships among the modules, then it will become a clumsy. It will be difficult for us to understand. Even we can't implement such a kind of modules properly. Okay, so that's what the importance of control abstraction. Next one is, when a failure is detected while executing a module, it is obvious that the modules below it can be possibly be the source of error. So this simplifies debugging. Okay, so whenever a module is failed, it simply we can say that a module which is present below that module would be the main reason for the cause of that failure. So it simplifies the debugging. What do you mean by debugging? Identifying the errors. This is done once the testing is completed, the debugging is done. So here we try to identify what are the main causes for these for the errors, and then later we try to rectify those errors. Okay, so during debugging phase the errors are termed as bugs. Okay, so this is how a layer design is, a modular and hierarchical design. And this is a design solution which is exhibiting poor modularity and hierarchy. So here in the modular and hierarchical design, here each and every modules, that is the call relationships among those modules, are represented in a tree-like structure, and here the lower layer modules cannot make a call to the modules that are present in the higher layers. That means the lower layer modules are not aware of the presence of higher layer modules. But if you consider this second design, can you understand it? Can you understand how the calls are made between these modules? So it's very difficult for us to understand, and it will also increase the implementation complexity. Okay, so that's what the importance of layered modular and layered design. Okay, coming to the modularity and layer design. So how a modularity is obtained. Okay, now that one let us see in this topic. Okay, A layered design can make design solution easily understandable. Since to understand the working of a module, it would at best have to understand how immediately lower layer modules work without having to worry about the functioning of the upper layer modules. A layer design can make the design solution easily understandable because to understand the working of a module, one would at best have to understand how the immediately lower layer modules work without having to worry about the functionality of the upper layer modules. That means in order to understand a module, it's enough to understand the modules in the lower layer. No need to understand the modules in the higher layer. Okay, so that happens only whenever there is a layer design. So if at all you want to understand this module, then it's enough to understand the modules which are below it. We no need to worry about the module which is present above it. But if you consider this design, if at all you want to understand this module, okay, so in order to understand this module, you need to understand the modules to which the calls are made, or to the modules which is it is exhibiting the dependency. Okay, so that means this module is making a call to this module, and it is making a call to this module. It is making calls to several modules. That means there are a lot of interactions between various modules, between this module and the various modules. So in order to understand this single module, you need to understand all these remaining modules also. So that's nothing but you need to understand all the modules set together. So can you break a bunch of sticks at a time? No. In the same way, you can't understand all the modules at a time. Okay. Good module decomposition is indicated through high cohesion of individual modules and low coupling of modules with each other. So that means we can have a good module decomposition if at all there is a high cohesion of individual modules and low coupling of modules with each other. So there should we are measuring this cohesion within a module, within an individual module, and we are measuring the coupling among various modules. Now let us see what is this cohesion and coupling. Okay. So coming to the cohesion, a cohesion is a measure of functional strength of a module. So that means in a module generally we will be having some set of functions. Okay, if all these set of functions are performing a single task, that is they are working for a single task, then we can say there is a high cohesion among those modules. So that's what a cohesiveness is. That's what the functional strength of a module. Okay, the cohesion is nothing but the measurement of functional strength of a module. Okay, and coming to the coupling between two modules is a measure of degree of interdependence or interaction between the two modules. If at all there is a lot of interaction between two modules, then we can say there is a high coupling. If at all any modules are having higher interactions, then can we understand them properly? Higher interactions in the sense we will be having the module structure in this manner, this second one. Okay, so can we have understandability in this design? No. Okay, so that means there should be low coupling. There should be high cohesion and low coupling. Okay, when the functions of a module cooperate with each other for performing a single objective, then the module has good cohesion or high cohesion. And if the modules either do not interact with each other at all, or at best interact by passing no data or only a few primitive data items, then they are said to have low coupling. Okay, do you understood? Good cohesion means all the functions within a module should perform a single task, that is they had to work for performing a single objective. Okay, so then we can have a good cohesion or a high cohesion. And coming to the low coupling, See, coupling is always between modules. Okay, so whenever there is no interaction among the modules, or whenever there is a little interaction uh, among the modules, like just by passing the data, or only by passing few primitive data items, then we can say there is a low coupling among those modules. Okay, so finally we can come with the output like a module having high cohesion and low coupling with other modules is said to be functionally independent of other modules. Coming to the advantages of functional independence. The first one is error isolation. Whenever an error exists in a module, the functional independence reduces the chances of error propagating to other modules. Since that module is having less interactions with the other modules, if at all an error has occurred in one module, then it will obviously affect only that module. Okay, so in that manner we can isolate the errors. Suppose if at all there is a high coupling in the sense there is a lot of interaction among the modules. Okay, and if an error has occurred in one module, obviously it will lead to the errors in the rest of the modules also. Okay, so that's what the importance of functional independence. Functional independence, when we can have functional independence whenever there is a low coupling. Okay, next one is reuse. Okay, whenever there are less interactions among the modules, that is when a module is not depending on other module. Okay, so we can isolate it and we can reuse it again. That means we can have the reusability nature. Okay, next one is understandability. Obviously, yes, if at all a module is isolated, that is, if at all a module is not having less dependencies with other modules, then it will be easier to understand it. Okay, that's what layer design. Okay, now coming to the classification of cohesiveness. So, based on the functional strength among the module, this cohesion is classified into these many types, various types like functional cohesion, sequential cohesion, communicational cohesion, procedural cohesion, temporal cohesion, logical cohesion, and coincidential cohesion. Okay, so already we know that cohesiveness is nothing but the degree to which different functions of a module cooperate to work towards a single objective. Okay, by examining the type of cohesion exhibited by a module, we can roughly tell whether it displays high cohesion or low cohesion. So that means by identifying what kind of cohesion is existing between the functions in a module, we can say whether there is a high cohesion or low cohesion. So if at all in a module if it is having a coincidental cohesion, then it indicates a low cohesion. See, the degree of cohesion is increasing from coincidental to functional. That means if at all a module is having functional cohesion, it indicates that there is a high cohesion in that module. Okay, so that's why we need to classify the cohesion among the modules. But do you understood? So just by understanding the type of cohesion, we can tell what is the degree of cohesion in that module. Okay, now let us see what do you mean by these various classifications of cohesions. So first let us start with the coincidental cohesion. Okay, so a module is said to be coincidental cohesion if it performs a set of tasks which related to each other very loosely. So that means here the module is having a set of functions and in which the functions are not performing for for a single objective. Okay, so we can say that here randomly picked functions are grouped to form a module. Okay, for example, let us consider this in this figure part B. Okay, so here we are having a module and the name of that module is managing book lending. Okay, and the functions managing book lending in the sense like whenever you are using a library management system, that is automated library management system. Okay, so there you issue for a book, that is you want to lend a book from the library. So in that case certain functions are to be exhibited. Okay, so now in order to lend a book, So these are the functions that are to be executed. That is issue book, return book, query book, find borrower. Okay. So these are the functions. All these 4 functions are working for a single objective, that is for managing book lending. Okay. Now see figure A. Sorry. Now see figure A. Okay. So here the module name is random operations, and in this module we are having certain functions like issue book, create member, compute vendor credit, request librarian leave. Is there any relationship among these functions? So issue book is related to the managing book lending. Create member is related to the whenever you request for the creation of library membership. And compute vendor credit is related to the whenever you had purchased a book, you need to pay whenever you need a membership in the library, you need to pay some amount, right? So that one, okay, that particular task is performed by this function. And request librarian leave, it's completely related to the librarian person. Okay, so here these all these 4 functions are performing different tasks, that is they are very loosely related to each other. Okay, so now the cohesion, this kind of the cohesion between these functions is called as coincidental cohesion. Okay, coincidental means something, the functions are coincidentally, various functions are coincidentally picked and kept in a module. Okay, so here there is a very low cohesion. Next, coming to the logical cohesion. A module is said to be logically cohesive if all the elements of the module perform similar operations like error handling, data input and data output, etc. So if at all any set of functions in a module are performing similar operations, that's they are not working for a single objective, but they are trying to perform a similar operations. Okay, then the cohesion among those modules is nothing but logical cohesion. For example, a module that contains a set of print functions to generate various types of output reports such as grade sheets, salary slips, annual report, etc. Okay, here even though we are printing different kinds of outputs, all these are nothing but performing the single operation, that's nothing but they are outputting the reports. The grade sheet is a kind of report, salary slips is a kind of report, annual report. Okay, that is logical cohesion. Coming to the temporal cohesion. A module contains tasks or functions that are related by the fact that all the tasks or functions must be executed in the same time span. That means if at all any set of functions are to be executed in the same time span, then the module is said to be possess temporal cohesion. For example, when a computer is booted, several functions like initialization of memory and devices, loading the operating system, etc. are to be performed in a same time span. Okay, so then we can say there is a temporal cohesion in this module. Okay, next one is procedural cohesion. A module is said to possess procedural cohesion if the set of functions of the module are executed one after the other, though these functions may work towards entirely different purposes and operate on very different data. Procedural cohesion in the sense, here we are having a set of functions in the module, and these set of functions are to be executed one after the other. Suppose we are having function A, B, C. Only after the execution of function A, function B has to be executed, and only after execution of function B, function C has to be executed. So that means there is an order of execution among these functions. Okay, so now we can say there is a procedural cohesion among these functions. For example, let us consider we are having certain functions in a module like login function, place order, check order, print bill, update inventory, logout. Okay, all these functions are to be executed in a sequential manner. That is, first we log in. Then after log into the, like, let us consider any Flipkart or Amazon account. Okay, you are logged into your Flipkart account. Then you place a order. Only after placing the order, that is only after the execution of this task, we go for the check order. Okay, Next, after check order, print bill. Only after printing the bill, your inventory is now updated. So once this task is done, then you can log out from your Flipkart account. Okay, so here these are the functions that are to be executed in a sequential manner. Okay, so this comes under procedural cohesion. Next, coming to the communicational cohesion. A module is said to have communicational cohesion if all the functions of a module refer or update the same data structure. If all the functions are referring to the same data structure, even though they are performing various operations, if at all they are using the same data items, then that kind of cohesion is called as a communicational cohesion. For example, let us consider a module named student, which is having set of functions like admit student, enter marks, print grade sheet, access. Okay, all these three functions access and manipulate data stored defined in an array named student records. Okay, whenever admit student function is executed, obviously that student details are entered in the student record array itself, and whenever any enter marks function is executed, again the same thing is updated in the student record itself, and whenever print grade sheet function is to be executed, obviously it needs this student record itself. So that means here these three functions are related by a single data item. Okay, that kind of cohesion is called as communicational cohesion. Next one is sequential cohesion. A module is said to possess sequential cohesion if different functions of a module execute in a sequence and the output from one element of the sequence is input to the next. See here, identify the difference between the sequential cohesion and the procedural cohesion. In the procedural cohesion, the functions are executed one after the other, but we are not bothering about their outputs. Okay, the output of one function is not given as an output to the other function. But coming to the sequential, here all the functions has to be executed in a sequential manner, and the output of one function is given as a input to the other function. Okay. For example, let us consider in an online store, consider that after a customer requests for some item, it is first determined if the item is in stock or not. So in this case, if the functions create order, check item availability, place order on vendor are placed in single module, then the module would exhibit sequential cohesion. So how? So coming to the first create order. So create order in the sense you had placed some order. So the outcome of this create order is nothing but some product. Let us consider some mobile phone. Okay. So once the order is created, first it has to check whether that mobile phone is in availability mode or not, that is whether it is available in the cart or not. Okay, so if it is available, then you need to place an order, place order on vendor. What you will place? So whatever the output you had got from check item availability, that is now taken as an input by this function, and we place an order on that particular, using that input we place an order. Okay, so now create order output is nothing but the mobile phone. The same mobile phone is given as an input to check item availability, and based on its output, then we are going for the place order on vendor. Okay, so here the functions are executed in a sequential manner, and at the same time the output of one function is given as input to the its immediately next function. Okay. Coming to the last category, that is functional cohesion. A module is said to possess functional cohesion if different functions of a module cooperate to achieve a single function. That means here they work for performing a single objective. Okay, such a kind of cohesion between the module is nothing but the functional cohesion. For example, a module containing all functions like compute overtime, compute work hours, compute deductions, etc. to manage an employee's payroll. That means in order to calculate the employee's salary, we need to execute all these three functions. Okay, that is compute overtime, compute working hours, compute compute deductions. Okay, only after the execution of these three functions we can get the correct salary amount of that particular of that employee for that particular month. Okay, so that means here all these three functions are working for a single objective. Okay, such a kind of cohesion is called as a functional cohesion. Okay, so with this I will end up this session. In the next session let us continue with the classification of coupling. Thank you, ma.